Hello, everyone. Good morning. Yeah, thank you for joining today's webinar. So I'm Tim Wang, co-founder and the CEO of Timeplus. So join me today is Gang Tao, our co-founder and the CTO. So we know the everybody calendar are mass. So I promise today that our webinar is not another sales pitch. We try to keep in the session engineer to engineer. So today we're going to talk about security detection specifically. So we all know the security fundamental is a data problem. So today we will go through the real architecture problem and looking at a real world use case and talk us through the solution. So most important, exciting thing, Gang is going to show a code and a demo so you can see the whole engine under the hood. So it's going to be a lot of fun. So hopefully it can change how you think about this real-time correlation and the control layout for security detection. So moving the existing post-modern analysis to proactive real-time defense. A bit quicker introduction about ourselves. So the co-speaker Gang Tao is my co-founder and CTO. So his background is pretty much for software data visualization. So before TimePlus, he was the principal engineer for Splunk, the machine learning and data platform team. I'm Tim. I spent over 20 years building the data platform. So most recently leading engineer team at Splunk, SAP, and EMC. So, but another thing that despite Gang is actually he's a huge fan of AC Milan. So actually, I'm the Inter Milan. So we do have some common thing. We spent a decade at a place like Splunk. We're building the data platform. Probably most of you might use today. So we're a practitioner, so just like you guys. So back at Splunk, so we have built the index first and index everything, the log search engine. It was right too for the last decade. But this monolithic query-focused design actually is hitting the physical limit. The math actually has simply changed. So we didn't start Timeplus to build another dashboard or maybe another central place for all the data. So we start Timeplus we saw the detection gap widely from inside. So we realized if you have waiting for data to hitting a disk or get an index before you ask a question, so you already lose the race against a modern attacker. So first of all, let's just stop a second, acknowledge a stunning new reality for security defense world. So looking at this dashboard, it's a time to exploitation from zerodayclock.com. In 2028, 2018, you had a 2.3 year buffer to find a bug and patch it. So looking today, the window has collapsed to the 1.1 days only. So we project to hit a 1 hour milestone this year. So think about it, if it's 1 hour from disclosure to global exploitation, if your data platform spend 20 minutes for injection, for indexing, so you probably already lose a 30% of your survivor window before a single human even look at the screen. So that's a new reality. So you see, so we already talked about the 1 day, 1 hour exploitation war. And we also see the attacker automate transition from access to execution only 22-second handoff. And according to CrowdStrike 2025 report, the fattest lateral movement, the breakout is down to 51 seconds. So the hard truth is all the attacker move in the second. So actually the user valid credential. So the 79% is a malware-free infiltration. So we're literally defending the days while they're actually attacking the second. So if your attack isn't happen in flight, if you're not doing security, right? So if you think about a 22-second handoff is scary, sounds scary. But looking at what happened when you add AI as attack chain. So this Anthropic report from later 2025, that isn't a theoretical white paper. It's the first documented case of a fully AI orchestrated cyber espionage campaign. So we're talking about its adversary is targeting over like 30 organizations simultaneously. This machine speed chain wasn't just a smarter fish. So they use AI agent to chain together with existing attack tool, scanner, and all that kind of thing. So AI handle the entire friction heavy part of the life cycle. So this totally everything happen in the machine speed. So why does this matter for architecture? So when the human focus on high level strategy, the AI handle the groundwork for like a pivoting, a lateral movement in second. The hard truth is you cannot fight a machine speed threat with a human speed query. So if your defense rely on the human analyst running a search on a data lake, you're probably already lost. So when the attacks are automated from start to finish, your detection response probably have to automate at the pipeline or injection layer. So the detection window collapsed with this massive machine scale and the speed. So look into the architecture. So we are developers. So you see the traditional SOC architecture is very typically connect all the syslog, endpoint, and everything, the data injection. So that goes through the very long injection and the processing indexing pipeline. And then they can run the scheduled search and the rules. And, and security analysts, operation analysts that probably do correlation after the storage. And finally, that triggers some a lot after the fact. So this architecture, we saw the fundamentally it falls short. So because the raw logs actually flow into the SIEM indexes the data. An analyst then run filtering transformation. So so by the time a pattern surface, the minutes actually is pretty past. So thousands of events have already injected in the store. That also costs huge money. So, and the worst, the attacker may have already succeed. So the detection logic itself usually is fine, but real bottleneck is when and the will that logic is wrong. So we actually really like consider the new architecture rather than maybe put everything injection into the one single storage and then run query. We consider the raw log. They can maybe add the control and the transformation correlation layer. They can do the correlation context detection route in the fly. So, and then they can route into the multiple storage. So including data lake, a SIEM, SOC platform. So this platform actually definitely like sitting between the raw log and the downstream install. So this layer actually really like can to improve the data quality and also to reduce the data size and also do real-time correlation. So that's a really fundamental the architecture shift. We call federation the architecture for the new modern the SOC, the SIEM model. So, so let's talk about one specific example. So we talk about here is just real-time correlation, dynamic correlation. So this capability actually is we put it like a just one the background is here. Just so usually we for a lot of the network data, the IP data, how to detecting high traffic from one IP address. But sometimes just one single logged item is not useful. So what matter here is whether the behavior is really abnormal for the specific entity at the specific time window, a moment. So if you answer this question, and sometimes we actually consider that's a little bit more context we have to connect, correlate. For example, how to do live aggregation over last maybe 5 seconds, it's a short time window. And how to calculate the historical, actually dynamic baseline. So for example, like a minutes, hours in, so, and this third step probably do a lot of real-time correlation. So how about the live data compare the baselines that get the new threshold? So finally, the threshold. Threshold is actually pretty dynamic. You cannot put like a fix the threshold the rules there. So you have to adapt per entity rather than just rely on the fixed number there. So I think a lot of maybe ask the question. So existing tool, how to handle this? Back to the Splunk. So we know the Splunk is a fantastic tool for retrospective analysis. To run the query. So that's a tip, but that's maybe they can talk about the same logic, but actually foundation actually implementation is definitely is very different. So this underlying is a search after storage as we talk about. So that make a lot of correlation actually super heavy and expensive, and critically it's not real time. Well, in general, so Splunk answer this question actually after data is stored. And Cribble probably is another fantastic tool for security data pipeline. So we know that Cribble is very strong, for data filtering, the routing normalization when the events pass through. But we consider, the new this kind of control layer, they have to do more. For example, like correlation, what happened? So that's something I think Cribble hits a wall quickly in the new SOC environment. So in general, the Cribble decide where data goes, routing, and the data reduction. So let's go to the Timeplus today. So we actually Timeplus actually can calculate a lot of live the data in the baseline very continuous way. And that they can maybe make a real-time join correlation happen when data is still in motion. So that can keep a lot of state. Detection can find the moment when threshold is crossed. This output actually can route into multiple downstream. They can send to the SIEM. They can to the central like the data lake. So in general, template really determine where data means why it's still moving. So that's we talk about this kind of architecture. Actually, for templates, actually it's not a really hypothetical, so architecture, assumption. So actually, it's a real world use case. So one of our, current the customer is one of the world's leading entertainment platform. They actually use a Timeplus as their real-time security context control layer that solve the cyber threat detection real time. They actually evaluate a lot of the data platform or database or SIEM detection, but finally that they're choosing the Timeplus. So now they can able to handle millions of events per second. So from the IP fixed flow data, they can track any of the baseline, the hundreds of thousands of unique IP simultaneously. That's a huge, a lot of the high cardinality data. And at the same time, they can detect this threat in seconds rather than just minutes or maybe even longer. And finally, that can run hundreds of concurrent rules. So these are rules including like real-time correlation, dynamic baseline comparison, and also even during the massive traffic spike. So the right chart actually outlines a simple is a diagram. So we actually compare 5 seconds to compare the 5 minutes. The aggregation. The most critical thing is that everything is dynamic here. So yeah, we talk about architecture, talk about the use case. I think the next one probably is the most exciting part. So my co-founder, CTO, the Gang, so we'll show a demo, the real very exciting demo. So now I hand over Gang.
Thanks, Tim. First, I'm going to show you how we read. We are using the Cisco ASA log data. The log is sending to Rapanda Kafka cluster, and we will have a log processing pipeline to extract all the information from the raw logs to a structured Timeplus stream. You see, we have this Cisco ASA logs topic, and there's a simulator generating the ASA logs in the real time. You can take a look at some of those data, which is sending to the Kafka topic in real time. And in Timeplus, we have this data processing pipeline in SQL. So first, you can see here, we start with here is a ASA log stream, which is actually a external stream. And then we have two materials view to do the log parsing and the flatten the log into a structure log. Let's take a look at how this pipeline works. First, this is the Kafka external stream. We just read the raw message from the topic, and if you query this external stream, you get all the raw logs. You see, this is the ASA raw logs. And then we have a materials view that do the parsing. So this first parser, we just pass the according to the syslog format. We get all the syslog fields, including ingest time, log stand, timestamp, device name, severity, and message ID, something like that. And then with this parse log, you can see we already get a structure log with all the syslog format. Still, the ASA message is quite different because different message ID share different format. So in next step, what I'm going to do is actually we want to extract more meaningful fields used for later DDoS attack rules. You can see we actually leverage a grok pattern for each different IDs. Then we extract all the details information, for example, the source IP, the source port, and all the details information. So as the grok return a map, so we just flatten the map into a big flattened structure table like this. So you can see we get all the fields. So eventually we have another IV to do the flattening and more structure field extraction. You can see. So now we have a flattened table, flattened Timeplus stream that contains everything, the details information of the ASA logs. So that's why we have this two MV. So with this two materials view, we actually have a keep extracting, do the ETL, do the data extraction. So if you query this flattened extracted ASA logs, we get a real-time Cisco ASA logs with all the fields extracted. So based on these extracted data, what we can do is actually we can start building this real-time control layer, the security DDoS attack detector with this pipeline. This is the DDoS detecting pipeline. Let's take a look how it works. So first we read the flattened logs. We just filter out the fields we interested in. So in this case, we are interested in the source IP, destination IP, and the bytes from the network flow, the content size. So because these are the key fields that will decide whether there's an attack is happening. A DDoS attack usually means there's a lot of source IP, there's a lot of network flows from a specific source IP. If we take a look, this is a real-time network flow data. We got all the source IP, destination IP, and network flow size. These are the fields we are going to use to detect whether there is an attack happening. So next, what we are going to do is we are going to show the pipeline. We actually contain two parts. The first part is actually a live 5-second stream. We use a 5-second hopping window to get the total bytes sent from the specific IP. So what we are doing is actually we do a 5-second live hopping window aggregation. You take a look at this. So we do hopping window with a 1-second slide, and every 5 seconds we do an aggregation for this live stream. We get the total live bytes sent by some specific IPs. So that's the live stream. To detect whether some attack is happening, what we are going to do is actually we need to compare this bytes to a baseline. So you can see this is the if you take a look at the live stream, you can see all the source IP, the 5-second live bytes from this source IPs. So, and next we are going to build a baseline. And the difference is the Timeplus baseline, we use a multiple stream that keep aggregating the historical data, right? So this means we want to know the normal behavior from all the historical data, but this data is actually not a static aggregation, static statistic. It's actually a keep changing one. So that means it keep changing based on your all the live stream. So let's take a look at this materials view aggregation. It's actually a tumble window with 5 seconds, and we get all the average SIEM bits in a 5 second window, right? So then we get a normal behavior. Say for a specific 5 second window, what's the average total bytes sent by specific IP? And we actually sort by all the IP. So that means we have a lot of changing baseline. Similarly, we want to build something more advanced. We actually build the hour of the day. We know what's the normal behavior for specific time range during a day. So for example, in the evening, what's the pattern of this South IP behavior, or in the morning, maybe it behaves different. So, but we build a more flexible timeline of average 5 second beats in during a day for specific time range. So with this baseline is actually keep changing, right? Because with this mutable stream, every time you get new data, this baseline is an aggregation of all the historical data. So it's keep changing. So that means when we do the joining, we got a comparison, a correlation between the current live stream behavior and the historical baseline of all the average 5 second bits and average 5 second bits totally for specific hours. So we do a joining between this live stream and our mutable stream, which is a historical pipeline. So we get two metrics: overall spike ratio compared to the overall 5 second baseline, and we got the average hourly spike ratio. So compared the current hour from historical aggregations. So, and if we query this context stream, you can see that we get the two metrics is overall spike and hourly spike. So normally this spike ratio is close to 1 or something close to 1. That means it is normal. But if there's attack happening on specific IP, this ratio can be grow very high. So that means maybe it's 10 times or even 100 times bigger. So then we can just check what is ratio. We just monitor this ratio. If there's a high spike, that usually means an attack is happening on specific IPs. So next we are going to check build the alert, right? So based on this context. So we in our alert, we actually trigger a Python function. In this case, every time you run this alert, so just query whether there's a spike change, and once the threshold exceed, we just call, hey, there's an alert. Please call this webhook. We send an alert to a webhook in this case. So that means by detecting the spike, we know there's some specific source IP is potentially having an attack because this IP has generated quite a lot of workflows, network flows. Then you can see actually this is the query realization in Timeplus. You can see there's some historical spike. Let me move this. So historical spike, that's because I was going running a test. We run a live query on this specific IP because I'm going to simulate an attack on this IP, on this source IP. So we have a simulator that similar. We are using the Timeplus stream as well. So there's an MV generating the attack stream. So the MV is paused. So if I resume this MV, it will generating a lot of network flows from the source IP. So let me run this MV. So resume this MV. Once I resume this MV, there's a lot of network flows generating from the source IP. You can see immediately Timeplus detect this spec, and the alert is sending to my dashboard alert server, and immediately we got this alert from this attack from this alert rules. So you can see how quick Timeplus can do this, because this is actually a use case from a reference from our real customer case. So you can see Timeplus can do very performant and real-time DDoS detection in this case. Similarly, we can do some other cybersecurity attacks, for example, the any other type using this SQL, everything in SQL, right? You can detect whether there's a brute force attack, there's some specific rules you can add to this one. The demo shows how Timeplus can use just pure SQL play as a real-time control plan for all your telemetry, right? So in this case, the telemetry come from Cisco SE log, but it can come from other data sources as well. So in Timeplus, we do real-time transformation, we do enrichment, correlation, stateful processing, and enrich the context. So these data, real-time data, can be used for different use cases. For example, your observability system or security system by do this correlation or reduce those noise. You can save quite a lot of cost because all the data sending to your system is those valuable signals. And for data lake or data warehouse, you don't have to do the correlation. Even data lake, you can do that. But if Timeplus can help you to do the correlation, it's much more faster to do the analysis in your data lake, right? Also, Timeplus can provide a real-time context for your AI applications. For all your agent, we can feed your agent with the real-time data context from all your operational data, right? So you don't have to search or index waiting for the rack. You get all the real-time data to using the data-driven way to run your agent. And last, you can also save some of the data to your cloud storage, because in that case you can save your cost because we process your data and you can save those data in cloud storage for cheaper storage. Okay, that's what I'm going to show you today. And we do have a live system called the Timeplus demo, timeplus.com. You can log in the system using username demo and password demo123, and you can try run this this demo I show in the demo. So for example, here is the real-time context stream I run today. If you run the query, you can see we get the real-time context overall spike and average spike are calculated in the real time. Okay, that's I'll hand over back to Tim. And any final words you want to share with our audience, Tim?
Yeah, thank you, Gang. It's very exciting. So this demo actually, as Gang mentioned, you guys can log into our demo server, so you can play by yourself and see how magic for this new control layer actually introduce a very unparalleled, the real-time detection, and also very flexible the logic you can define. Actually, use a very simple the SQL query language here. So that's sometimes we really really want to show today. So anyway, yeah, that's a probably stop here. So as these slides, so you can feel free to anytime you can join our Slack community and visit our website, and also we have the open source core engine component we call the Proton. So feel free to visit that Proton, give us a star. So thank you so much. Probably we stop here. Any question, or we can maybe answer some question if we have some. Yeah, I think that one question regarding to how are dynamic baseline bootstrap for new or ephemeral the entity. So how is a dynamic baseline bootstrap for the new entity? Is that, I think probably Gang, you can answer this question.
Yeah, sure. For the state management, Timeplus has an internal state management system. So I do have some blogs you can refer to at our website. But generally, we do keep state. State is keep in the memory, and we do periodically checkpoint mechanism to to make sure the state will not lost. But under the hood, we actually have a very high performance C++ based processing. So that means the high performance processing plus this state can make sure your processing is scalable. That in this case, for example, the DDoS case, there's millions or even more IPs. So for each IP, you can see we keep a state, right? So that's a large number of state. So we do have a lot of mechanism to make this scalable. One of the things you can check our blog for some of the technical details. But generally, it's highly scalable.
Yeah, thank you. So maybe the last question. So, because in general, the question is just about how does Timeplus handle the scalability, particularly during the massive maybe traffic spike or data spike. Maybe the question is just compare the traditional database, right? So how the Timeplus is so different, handle this spiky traffic.
Right. So in
Mhm.
today's demo, you can see that we actually using a multiple stream as the baseline. So this multiple stream is actually a keep changing stuff. So under the hood, the multiple stream keep a tree structure like a key value change. So for every key change, it keep the latest value. So it keep continually computing this threshold change. So that's super fast. Every time you have a new workflow, this threshold, this baseline is changing, right? It's keep computing. Compared to the traditional database, if you join into with the historic data, it's just one shot, right? You just run the query, get one, and get baseline and do the comparison. But in Timelapse, this threshold is keep changing because everything the net is data driven. If you have a network flow, new network flow, this baseline keep changing. So that's the quite different architecture.
Yeah, Sangha. Yeah. If you have some other question, welcome to probably just join our Slack community so they can ask any question offline so we can have deep dive there. So yeah, thanks so much for the join today's webinar. So I just wonder, it's kind of a notice we have the April, we have another webinar. Just probably talk about more, security and those kind of control layer for a lot of the new use case. So definitely, looking forward to see you next time. Thank you.
Thank you. See you next time.
Yeah. Bye-bye.